Welcome to 2.7 video lesson Algebra 2. The concept is absolute value functions and graphs, and we have 8 boxes to talk about today, so let's get right into it. Okay, the first idea is to just introduce to you what the absolute value parent function is. And the absolute value parent function in terms of an equation is written by the absolute value of x, which I'm sure you've all seen before. So if I make a table of values, let's say I have the value of -3, -2, -1, all the way up to 3, then the f of x, or the function output values, would be a value of 3, 2, 1, 0, 1, 2, and 3, because the absolute value of a number is always positive. That shouldn't be a big surprise. So if I take this table and make a sketch, at -3 I'd be up at 3, at -2 I'd be up at 2, at -1 I'd be up at 1, at 0 I'd be at 0, 1, 1, 2, 2, 3, 3, and so on. Then if I actually connected all of these dots here with a line that went on forever and ever, then I would, of course, get the nice pretty graph, which I've got for you over here, which is the good representation of the absolute value. So the parent graph, the points that you need to know are 0, 0, like 1, 1, or like 1, 1 in this case, and 2, 2. So you need to know the basic shape of the parent function, and it makes a graph. It makes the graph the shapes like a V, and this is the beginning of where we start to talk about how to move the absolute value graphs around. So this is the first part of understanding absolute value functions. Okay, in box number 2, we're going to understand how to translate, and the word translate just means to move the graph around. So we're going to learn how to translate the graph of f of x equals absolute value of x. There are 4 ways to translate a graph in this box. We can go up, down, left, or right. So let's first talk about how to move the absolute value graph up. In all 4 of these boxes, I've given you the basic parent function laid out in black. And then I'm going to talk about what this added value k does. So if I take the absolute value of f of x equals, f of x equals the absolute value of x, and then I add the number k. So if I add a constant onto the end of it, that's going to move my graph up however many k units is. So as an example, if I was trying to graph f of x equals the absolute value of x plus 2, then this whole entire graph would be shifted up 2 units. So if I add something on the back end of my function, if I add a positive value of k, it's going to move my graph up 2 units. Likewise, if I add a negative value of k outside my absolute value function, it's going to move my absolute value function down on the coordinate plane. So if I wanted f of x equals the absolute value of x minus 3, then each single point would be moved down 3. 1, 2, 3, 1, 2, 3, and so on and so forth. So the graph would end up looking like this. So this is how to move it down 3. So up and down are pretty straightforward. If I add a positive number on the back end, it moves it up. If I subtract a number on the back end, then I'm going to move it down. Left and right is a little more non-intuitive. Right, you'll notice that first of all, the k value is now inside the absolute value function. And if I'm moving something to the right, you'll notice that there's a minus sign before it. And if I'm moving something to the left, you'll notice there's a positive sign before it. The reason is because if I move something to the right, then I have to subtract off a certain number of values of k to get back to 0. So it's the opposite direction you think it would be. So as an example, if I wanted to graph f of x equals the absolute value of x minus 3, that would mean that whole graph would be 3 units to the right. So my new vertex sort of would be here, right? And my graph would look something like this. It'd be moved 3 units to the right. So a negative sign inside the absolute value function is going to move it to the right. A positive sign inside the absolute value function is going to move it to the left. So if I have absolute value of, say, x plus 1, then this whole graph would be moved over to the left 1 unit, like this. So box number 2 is all about up, down, left, and right, and make sure that you have all of these in your notes. Okay, here's box number 3. This is a U-try for box number 3. How will the graph of f of x equals x plus 3 compare to the parent function of the graph f of x equals absolute value of x? Okay, hopefully you got the right answer, and you said that the function f of x equals absolute value of x plus 3 will be translated 3 units to the left of the parent function absolute value x equals f of x, absolute value of x. So in the picture here, the black dotted line is the absolute value function, and the blue graph is the absolute value of x plus 3. Notice that it's been shifted 3 units to the left. All right, in box number 4, we're going to do an example together. And our goal is to be able to sketch the function absolute value of x minus 4 plus 1. So the first thing that we have to realize is that we're going to begin with the parent function, f of x equals the absolute value of x. And I've already graphed that for you over here on the left in the black dotted picture right here. That's the absolute value of x. Then we want to make sure that we understand, okay, that if I have a minus 4 on the inside, that's going to be 4 units to the right. All right, and then this plus 1 is going to be 1 unit up. So I'm going to take my vertex, my original point at 0, 0, and I'm going to move it 4 units to the right, 1, 2, 3, 4, and then 1 unit up. So my new vertex is going to be this location at 4, 1, and then every single point from there on out just acts like it normally does it takes the shape of the parent function. So the new sketch would be something that looks like this. So it's really important that you understand that the minus 4 on the inside of the absolute value function will make it 4 units to the right, and the 1 on the outside will make it 1 unit up. And then to go ahead and sketch the graph. Okay, box 5 is another you try. I have given you a picture, and I want you to come up with the equation that best fits this picture for absolute value. So write the equation for the following function, whose parent function is f of x equals absolute value of x. Hopefully you got the right answer of absolute value of x plus 7 and then minus 2 on the outside of your function. Why is this the answer? Because if my original graph starts at 0, 0, I'm going to move my vertex 7 units to the left. That is the plus 7 part. And then down 2 units, that is the minus 2 part on the end. So the correct answer was the absolute value of x plus 7 minus 2. Okay, in box number 6, I want to talk to you about vertical stretching and compressing of absolute value functions. So let's talk about stretching first, okay? Whenever you have an absolute value function, the absolute value of x, and I multiply it by a value of a on the outside, where the a is bigger than a 1, so a could be like 2, 3, 5, 10, 15, 1.8, anything like that. If your a value is bigger than 1 and you multiply it by your absolute value function, that is going to result in what's known as a vertical stretch. So let me give you an example of what that means and what that looks like. On the picture, I have the original parent function, f of x equals absolute value of x. That's your black dotted line right there. Then in the orange, I have the function f of x equals 2 times the absolute value of x. Now you'll notice that the a value of 2 is bigger than 1, so that means I'm going to have a vertical stretch. So in more context, what that really means is if I take an original point, like say for example 2, 2, and I run it through my new function here, then I would end up with the output of 2, 4. Reason being is because the absolute value of 2 is 2, and then I multiply it by 2 and I get 4. So you'll notice that the y coordinate has changed from a 2 to a 4, meaning that this point has been stretched up to that point of 2, 4. And that would be true for every single point. So what this is known as a vertical stretch. So again, if my a value is bigger than 1 and I multiply it by my absolute value function, it's going to result in a vertical stretch. Okay, let's compare that to a vertical compression. Again, we're taking an absolute value function and we are multiplying it by a number on the outside, but this time that number is trapped between 0 and 1. So it could be 1/2, it could be 1/3, it could be 2/5, it could be any number between 0 and 1. Obviously not 0 itself and not 1 itself, but a number in between. So let me explain to you in context what that looks like on the graph. So again, let's say I have the parent function in black dots, absolute value of x, and then I have this orange graph, which is 1/2 times the absolute value of x. So notice that the a value in this case is 1/2, and that number 1/2 is trapped between 0 and 1. So what it does is, let's take a point here, 4, 4. If I run it through my new function, it would translate to 4, 2. So again, the y value has been shrunk down to half as much. So that means that this new output for x is going to be down there at 2 versus up at 4. And what that does is that results in a vertical compression for all points. Kind of a tricky concept, but the thing that you need to know is that if your a value is bigger than 1, then you're going to get a vertical stretch. If you're multiplying by an a that's between 0 and 1, you're going to get a vertical compression. Okay, I have 3 graphs for you. I have the black graph here in dotted line, which is your parent function, absolute value of x. I have a red absolute value function, and I have a green absolute value function. Please answer the following questions. Okay, box number 8 is all about reflections of absolute value functions. There are 2 kinds of reflections, and it all depends on where the negative is in the absolute value function itself. So let's compare the negative absolute value of x versus the absolute value of negative x. So I want you to take very note of where the negative sign is. Let's talk about this first one here. If your negative sign is on the outside of your function, then that means you're going to have a reflection in the x-axis. If your negative sign is on the inside of your absolute value function, that means you're going to have a reflection in the y-axis. So let's talk about these more in depth. Let's say I have the negative absolute value of x plus 2. I have graphed the parent function in the black dotted line, and then I have the actual resultant of what you see here, the negative of absolute value of x plus 2. So how would I get that? So first, I would think about x plus 2 means I would move my entire graph 2 units to the right, or sorry, to the left, excuse me. And then the negative sign would mean I would flip the graph over across the x-axis, and that's how I would end up with the final graph that you see here. That one makes a lot of sense to most people. Part B is the one that trips everybody out because they say, well, wait, Mr. Doritos, check this out. This says that plus 2, but look at your graph is over there to the right. So how does that happen? So let me explain this one. So I'm noticing that the absolute value is on the, or the negative is on the inside of my absolute value of x. So what I would do is I would consider this just like a normal graph. I would do, what does x plus 2 look like, right? Well, that graph would look like this. I just figured that one out. It would look something like this, okay? Then, since my negative is on the inside, I would reflect this blue graph over the y-axis, and that is how I would get to this final green graph here. So this one is the tricky one, so be careful when you see that, because most students draw this graph where I did the first one, and they forget to reflect it over the y-axis. Okay, kind of a lot of information today, but we will practice more in class.